Welcome to our walkthrough of problem number 1632, rank transform of a matrix. In this session, we'll explore the problem statement, analyze a brute force approach, and discuss its complexities. Let's dive right in. In this problem, we're tasked with performing a rank transform on a matrix. The rank of an element is determined based on its relative order in its row and column. The smallest element in a row or column gets assigned a rank of 1, the second smallest gets rank 2, and so on. If two elements have the same value, they must share the same rank. Additionally, ranks must be as small as possible while ensuring this condition is met. The rank of an element depends only on the rows and columns it belongs to, not on other rows or columns. The goal is to compute and return a new matrix where each element represents the rank of the corresponding element in the input matrix. The input matrix can have dimensions up to 500 by 500, with values ranging from -10 to the power of 9 to 10 to the power of 9, so the solution needs to handle large inputs efficiently. Let's look at a simple example. Suppose the input matrix is a 2 by 2 grid with values 1, 2, 3, 4. The smallest value in the matrix is 1, so it is assigned a rank of 1. The next smallest value is 2, which gets rank 2. For the value 3, it is larger than all elements in its row and column with rank 1, so it is assigned rank 2. Finally, the largest value, 4, gets rank 3. The resulting rank matrix is 1, 2, 2, 3. Now, consider a different example where the input matrix is 7, 7, 7, 7. Since all elements are equal, they all share the same rank. In this case, each element is assigned rank 1, resulting in the output matrix 1, 1, 1, 1. Another example is a 4 by 3 matrix, 20, -21, 14, -19, 4, 19, 22, -47, 24, -19, 4, 19. This example highlights how ranks are assigned when there are both positive and negative numbers, as well as duplicate values within rows and columns. For the input matrix, 20, -21, 14, -19, 4, 19, 22, -47, 24, -19, 4, 19, the ranks are assigned as follows. The smallest value, -47, gets rank 1. The second smallest value, -21, gets rank 2. The ranks continue to be assigned in increasing order, ensuring that equal values within the same row or column share the same rank. For instance, the value 4 appears multiple times and is assigned rank 3 consistently. The final output matrix is 4, 2, 3, 1, 3, 4, 5, 1, 6, 1, 3, 4. Since the matrix size can be large, the algorithm must be designed to handle ranking efficiently. Let's consider some edge cases. For a single element matrix, such as 42, the output should simply be 1, since there's only one element. If all elements in the matrix are identical, for example, 5, 5, 5, 5, the output should contain all ones, as all elements share the same rank. When the matrix contains a wide range of values, such as -10 to the power of 9 to 10 to the power of 9, the algorithm must handle this large range without any issues. Finally, for sparse matrices with many duplicates in rows and columns, the solution must ensure that rank assignments remain consistent and correct across the matrix. These cases highlight the importance of designing an efficient and robust approach to handle all possible scenarios. To begin, let's consider the brute force approach to solving the rank transform problem. The intuition here is straightforward. We iteratively assign ranks to matrix elements by examining each row and column. First, we sort all the elements of the matrix globally by their values. Then, for each element, we compute its rank based on the maximum rank of elements in its respective row and column. This process repeats until all elements are ranked. However, there are some important observations to note. The rank of an element is determined by the relative order of all elements in its row and column, which means the dependencies can become intricate. Iterating through all rows and columns repeatedly to update ranks is computationally expensive. In terms of complexity, sorting the matrix elements globally requires m*n log m*n time, and the repeated rank updates across all matrix elements lead to a total cost of open parenthesis m times n close parenthesis squared. While this approach is conceptually simple and straightforward, it becomes impractical for larger matrices due to its high time complexity and inefficiency. Now, let's shift our focus to a more optimized approach that uses union find along with coordinate compression. The key intuition here is that the rank of an element depends only on the relative ordering of other elements in its row and column. This allows us to process the matrix elements in increasing order of their values, grouping cells with the same value, and efficiently determining their ranks. The steps are as follows. First, we use coordinate compression to group all cells with the same value together and sort all matrix elements by their values. Then, for each group of cells with the same value, we use a union find data structure to propagate ranks efficiently. Specifically, for each cell, we compute the maximum rank of its row and column and assign the next available rank to all cells in the group. Finally, we update the row and column ranks to reflect the newly assigned values. This approach ensures that ranks are assigned consistently and in the correct order while leveraging union find for efficiency. The complexity of this optimized approach is significantly better than brute force. Sorting all matrix elements by value takes m*n log m*n time. The union find operations, used for grouping cells and propagating ranks, are performed in m*n alpha m*n, where alpha is the inverse Ackermann function, which grows extremely slowly and is nearly constant for practical purposes. This results in an overall time complexity of m*n log m*n, making it highly efficient. One of the key realizations, or aha moments, with this approach is that ranks can be assigned in the sorted order of values, breaking the problem into independent subproblems for each value group. Union find allows for efficient handling of dependencies between rows and columns, ensuring that ranks are propagated correctly. While the implementation is more complex compared to brute force, the efficiency gains, especially for larger matrices, make this trade-off worthwhile. Given the considerations, the chosen strategy is the optimized approach using union find with coordinate compression. This method is computationally efficient for large matrices, achieving a time complexity of m*n log m*n. We selected this approach because the brute force method, while simple, is prohibitively slow for larger matrices. The optimized approach strikes a balance between efficiency and scalability, leveraging sorting and union find to handle rank assignments effectively. It also resolves edge cases, such as duplicate values within the same row or column, ensuring consistency in rank propagation. The main trade-off here is the slightly higher implementation complexity compared to the brute force method. However, the substantial improvement in performance, especially for large inputs, justifies this additional complexity. Ultimately, this strategy ensures that the rank transform is computed efficiently, maintaining correctness while scaling well to handle larger matrices. In this problem, we begin with a matrix of integers and aim to assign a rank to each element based on its value relative to others in the same row and column. The rank of an element must satisfy specific rules. It should be greater than the ranks of smaller elements in the same row or column, and equal-valued elements must share the same rank. This needs to be done consistently across the entire matrix. To tackle this, our algorithm starts with input parsing and initialization. First, we read the input matrix dimensions and initialize a rank array of size m plus n, where each entry starts at 0. This array keeps track of the highest ranks assigned to rows and columns up to a given point. Additionally, we structure the elements of the matrix into a list of tuples, each containing the value of the element, its row index, and its column index. This setup will allow us to efficiently process elements while maintaining rank consistency. The next step is to sort the elements of the matrix. By flattening the matrix into a list of tuples containing the value, row index, and column index, we can then sort this list by value in ascending order. Sorting ensures that smaller values are processed first, which is crucial because ranks are assigned incrementally, and smaller values must be handled before larger ones to maintain consistency. After sorting, we process elements in groups based on their value. For elements with the same value, we calculate their ranks together because they must share the same rank. To determine the rank within a group, we look at the maximum rank currently assigned to their respective rows and columns using the rank array. The rank for an element is set to the maximum of these values plus 1, ensuring that it is strictly greater than any smaller element in the same row or column. To efficiently manage rank propagation and ensure consistency across rows and columns, we employ a union find data structure. This technique allows us to merge the ranks of rows and columns that are interconnected by elements of the same value, streamlining the rank assignment process. Once the ranks for a specific value group are determined, we update the rank array for the associated rows and columns to reflect the newly calculated ranks. These updated ranks are then assigned to the corresponding elements in the matrix. This process is repeated for each distinct value group, ensuring that all elements in the matrix are eventually processed. As we handle each group in ascending order of value, the rank assignments remain consistent and accurate throughout. Finally, after all elements have been processed, we construct the resulting matrix using the ranks assigned during the algorithm. This updated matrix, where each element's value is replaced by its computed rank, is returned as the output. The key insights behind this algorithm are its systematic approach to rank assignment and the use of efficient data structures. Sorting the matrix elements by value is critical, as it allows ranks to be assigned incrementally based on value order. The union-find data structure plays a pivotal role in maintaining rank consistency by efficiently merging rows and columns that are interconnected by elements of equal value. Additionally, the rank propagation strategy ensures that an element's rank is always one greater than the maximum rank of any smaller element in its row or column, preserving strict monotonicity. The algorithm relies on three primary data structures: the rank array, which tracks the maximum rank assigned to each row and column, the union-find structure, which manages equivalence classes of rows and columns, and the sorted list of tuples, which organizes the matrix elements for processing. In terms of complexity, the sorting step dominates with a time complexity of O(m*n log m*n), while the union-find operations are nearly constant time, making the overall algorithm efficient and scalable for large matrices. To solve the rank transform of a matrix problem, we start by importing the necessary libraries and defining our solution class. Inside the matrix rank transform method, we first determine the dimensions of the matrix M and N. Next, we set up the data structures needed for the union-find algorithm, parent and rank. These will help us manage disjoint sets, where parent keeps track of the representative for each set, and rank helps balance the merging of sets. We then define the find function, which retrieves the representative of a given element while performing path compression to optimize future queries. The union function merges two sets based on their ranks, ensuring that the smaller tree attaches to the larger one to maintain efficiency. Finally, we prepare a default dict called value_to_positions, which will group all matrix elements by their values, mapping each value to the list of its coordinates in the matrix. We populate the value_to_positions dictionary by iterating over each element in the matrix. For each value, we append its row and column indices as a tuple. Next, we initialize row_max_rank and col_max_rank arrays to track the maximum rank assigned so far for each row and column. We also create the answer matrix, initialized to 0, to store the final ranks. Now, we process each unique value in the matrix in sorted order. For each value, we retrieve its positions and clear the parent and rank dictionaries to prepare for a new round of union-find operations. For every position, I, j, corresponding to the current value, we initialize its row and column as separate components in the union-find structure. We then merge the row and column components for all positions with this value, ensuring that all elements of the same value are part of the same connected component. Afterward, we calculate the maximum rank for each connected component by iterating through the positions again and finding the root of each component. The rank is computed based on the maximum rank of the rows and columns within the component. Finally, we assign ranks to each position in the matrix based on the connected components. For each position, I, j, we determine its component's root and calculate the rank as one greater than the maximum rank of its component. This rank is then stored in the answer matrix at the corresponding position. Simultaneously, we update the row_max_rank and col_max_rank for the current row and column to reflect the newly assigned rank. This ensures that subsequent ranks in the same row or column are calculated correctly. Once all values have been processed, the answer matrix, which now contains the rank transformation of the original matrix, is returned as the final result. Here, we begin by defining the solution in Java. The function matrix rank transform takes a 2D array, matrix, as input. We first determine the dimensions of the matrix, storing the number of rows in M and the number of columns in N. To implement the union-find algorithm, we create two maps, parent to track the parent of each element and rank to track the rank or depth of each set. These maps will help us efficiently manage the connected components of the matrix. Next, we define the find method, which recursively finds the root of an element and applies path compression to flatten the structure for efficiency. If the current element's parent is not itself, the parent pointer is updated to point directly to the root. Then, we define the union method, which merges two sets by connecting their roots. The union operation ensures that the root of the smaller rank set points to the root of the larger rank set. If the ranks are equal, we arbitrarily pick one root and increment its rank. This careful management of ranks ensures the union find structure remains balanced and efficient. Now, we group positions within the matrix based on their values. We use a map called value to positions to associate each unique value in the matrix with a list of its coordinates. By iterating through the matrix, we populate this map, effectively organizing the matrix elements by their values. Next, we initialize arrays rowMaxRank and callMaxRank to keep track of the highest rank seen so far for each row and column, respectively. We also prepare the answer matrix, which will store the final ranks. For each unique value in the matrix, we retrieve the list of positions associated with that value. Before processing these positions, we clear the parent and rank maps to reset the union find structure for the current set of positions. This ensures that the union find operations for each value are isolated, allowing us to handle each value independently. We then initialize the union find structure by creating separate sets for each row and column in the current value group, associating them with unique keys in the parent and rank maps. For the current set of positions, we now perform union operations to connect rows and columns that share the same value. By treating rows and columns as nodes in a graph, we use the union method to group them into connected components. After establishing these connections, we determine the maximum rank for each connected component. To do this, we iterate through the positions again, finding the root of each row or column using the find method. For each root, we calculate the maximum rank based on the highest rank seen so far in the corresponding row and column. This information is stored in a map called componentMaxRank, which associates each root with its maximum rank. These maximum ranks represent the highest rank that can be assigned to any element in the connected component, ensuring that rank assignments are consistent and adhere to the problem's constraints. Finally, we assign ranks to the elements in the current value group and update the maximum row and column ranks accordingly. For each position, we retrieve the root of its connected component using the find method and determine its rank by adding 1 to the maximum rank of the component. This rank is stored in the answer matrix at the corresponding position. We then update the rowMaxRank and callMaxRank arrays to ensure that subsequent value groups respect the updated maximum ranks. By processing the values in ascending order, we guarantee that the rank transformation adheres to the problem's requirements. Once all values have been processed, the answer matrix contains the rank transformed version of the input matrix, which we return as the final result. To solve the problem, we begin by analyzing the input matrix. Here, the dimensions are 2 by 2, so m and n are both set to 2. We initialize two lists, row_max_rank and call_max_rank, both filled with zeros. These will help us keep track of the highest rank assigned to each row and column. Next, we group the matrix values by their positions. This creates a dictionary where each unique value points to a list of its coordinates in the matrix. For instance, the value 1 is found at position 0, 0, and so on for the rest of the values. Now, we process these values in ascending order, starting with 1. For value 1, we initialize a union find structure to handle connected components. Each row and column associated with the positions of this value is treated as a separate node. For position 0, 0, the row component 0, R, is unioned with the column component 0, C. After computing the maximum rank in this component, we assign the next rank, which is 1. The row_max_rank and call_max_rank are updated to reflect this, and the rank is assigned to the corresponding position in the matrix. At this point, the intermediate result is 1, 0, 0, 0. Now we move on to value 2, which is located at position 0, 1. Using similar union find operations, we determine the connected components and calculate the maximum rank, which turns out to be 2. We update the rank for this position and adjust the row and column maximum ranks accordingly. This results in row underscore max underscore rank becoming 2, 0, and col underscore max underscore rank becoming 1, 2. The updated matrix is now 1, 2, 0, 0. Next, we process value 3, found at position 1, 0. After unioning the relevant row and column components and computing the maximum rank, the value 2 is assigned to this position. The row and column maximum ranks are updated to 2, 2, and 2, 2, respectively, and the matrix becomes 1, 2, 2, 0. Finally, for value 4 at position 1, 1, the rank 3 is assigned, and the maximum ranks for rows and columns are updated to 2, 3, and 2, 3. The final result for this example is 1, 2, 2, 3. In the next example, we consider a matrix where all values are the same. Here, the value 7 is present at all positions. The value underscore to underscore positions dictionary groups all these positions under the key 7. Using union find, we treat all rows and columns as part of the same connected component. For instance, the row component 0, R, is unioned with the column components 0, C, and 1, C, and similarly for the other rows. Since all positions share the same component, they are assigned the same rank, which is 1. The row and column maximum ranks are updated to 1, 1 for both, and the final matrix becomes 1, 1, 1, 1. This demonstrates how union find efficiently handles cases where values are repetitive, ensuring that all connected components properly share the same rank. For the final example, we look at a more complex matrix where values vary significantly. The values are processed in ascending order, starting with 1 and progressing through 2, 3, 4, 5, and finally 6. As we process each value, we use union find to group rows and columns associated with that value, ensuring that connected components are properly identified. The ranks are computed based on the current maximum ranks for the rows and columns involved. For example, after processing 1, the resulting matrix shows a rank of 1 assigned to its position. Similarly, after processing 2, the rank 2 is assigned to the appropriate positions. This continues until all values are processed, and the final matrix becomes 4, 3, 2, 1, 2, 3, 6, 5, 4. Key insights from this solution include the importance of processing values in order, ensuring rank consistency, and leveraging union find to handle connected components efficiently. This ensures that the rank constraints for both rows and columns are always satisfied. The time complexity of this solution is determined by several key operations. First, we start with sorting the values in the matrix. Since there are m times n total elements in the matrix, sorting them requires O, m asterisk n, asterisk log, m asterisk n, time. This is because sorting is typically performed using algorithms like merge sort or quicksort, which operate in n log n time complexity. After sorting, we move to processing each unique value in the matrix. Here, the matrix positions corresponding to each unique value are grouped together. If there are k unique values, and each value appears p times on average, the total number of positions processed across all groups is still m times n. This step ensures that we efficiently handle all elements in the matrix without redundant operations. Union find operations are performed next. For each unique value in the matrix, we use union find to group positions with the same value, identifying connected components. Thanks to path compression and union by rank, each union or find operation is nearly constant time, with an amortized complexity of O, alpha, p, where alpha is the inverse Ackermann function. While this function grows extremely slowly and is practically constant for all realistic input sizes, the total cost of union find operations across all elements is O, m asterisk n asterisk alpha, m asterisk n. This simplifies to O, m asterisk n, since alpha is very small. Additionally, we need to update the ranks for each position. This involves iterating over all positions in the matrix, which takes linear time, i.e., O, m asterisk n. When we combine these steps, sorting remains the most computationally expensive operation, leading to an overall time complexity of O, m asterisk n, asterisk log, m asterisk n. Now, let's discuss the space complexity of this solution. The total space complexity is O, m asterisk n, and here's why. First, the union find data structures, such as the parent and rank dictionaries, store one entry for each row and column in the current group of positions with the same value. In the worst case, this requires O, M plus N, space per unique value. However, since these dictionaries are reused for each unique value, the space usage remains constant and does not accumulate. Next, the value to positions mapping stores a list of all positions for each unique value in the matrix. This requires O, M asterisk N, space because it directly corresponds to the total number of elements in the matrix. Additionally, the row underscore max underscore rank and col underscore max underscore rank arrays store the maximum ranks for each row and column, respectively, requiring O, M plus N, space. Finally, the result matrix, which stores the final rank transform, uses O, M asterisk N, space. These components together dominate the space complexity, which is linear in the size of the matrix. The total space complexity is dominated by the O, M asterisk N, required for the mapping and the result matrix. To put this into perspective, consider a brute force approach. In such an approach, we would repeatedly iterate over the matrix, updating ranks iteratively until no changes occur. This could take O, open parenthesis M times N close parenthesis squared, time in the worst case, as each element might need to be compared and updated based on all other elements. By contrast, the optimized approach we've presented here avoids redundant computations. Grouping elements with the same value and processing them collectively using union find allows us to efficiently determine ranks for connected components. Additionally, sorting the matrix ensures that rank updates propagate in the correct order, eliminating the need for repeated passes over the matrix. This optimization highlights the significant improvement in time complexity compared to the brute force solution. Finally, let's analyze the best, average, and worst case scenarios. In the best case, where all elements in the matrix are unique, the union find operations are minimal. However, the sorting step still dominates, resulting in a time complexity of O, M asterisk N, asterisk log, M asterisk N. In the worst case, where all elements in the matrix are the same, union find operations become more extensive as we process a single large connected component. Despite this, the overall complexity remains O, M asterisk N, asterisk log, M asterisk N. On average, the time complexity is also O, M asterisk N, asterisk log, M asterisk N, as the sorting step dominates regardless of the distribution of values. From a mathematical perspective, sorting is the most computationally expensive operation with O, M asterisk N, asterisk log, M asterisk N, complexity. While union find operations are linear due to path compression and union by rank, their contribution is overshadowed by the sorting step. This justifies the overall time complexity as O, M asterisk N, asterisk log, M asterisk N. When working on this problem, there are several common mistakes to watch out for. First, skipping edge cases is a frequent issue. For example, failing to handle scenarios like empty matrices, matrices with only one row or one column, or matrices with duplicate values can lead to unexpected errors. These edge conditions often break naive implementations, so it's critical to test against them. Next, inefficient sorting can be a major pitfall. Sorting the entire matrix globally for every operation introduces unnecessary overhead. Instead, you can optimize by processing rows or columns individually, which significantly reduces complexity. Another mistake is not using the correct data structures. For example, relying on arrays for tasks that require fast lookups or updates, like rank assignments, can slow down your solution. Opting for hash maps or priority queues instead can improve runtime efficiency. Finally, avoid overcomplicating the rank calculation. Adding unnecessary loops or conditions not only increases the chances of introducing bugs but also makes your code harder to debug. Focus on keeping the logic clean and straightforward. Also, it's important to consider space complexity. Using excessive auxiliary storage can be problematic, especially when working with large matrices, as it may lead to memory overflow. Instead, aim to minimize auxiliary space usage, targeting O1 where possible. Now, from an interview perspective, there are a few insights worth noting. This type of problem often revolves around sorting, ranking, and leveraging data structures. Recognizing these patterns will help you efficiently combine techniques. Interviewers may also ask about trade-offs, such as choosing between time and space complexity. Be prepared to explain your decisions, such as why you might use hashing over sorting. Another point to keep in mind is optimization triggers. If your brute force solution exceeds O(n squared or O(n cubed for large input sizes, it's a red flag that you should optimize by reducing redundant operations. Lastly, always test your solution thoroughly, covering small cases, edge cases like single rows or columns, and large cases to ensure it scales well. This problem is also closely related to other problems that you might encounter. For example, LeetCode 1331, which involves the rank transform of an array, shares similar concepts. Problems like LeetCode 1202, smallest string with swaps, and LeetCode 200, number of islands, also involve techniques like grouping or traversal that can be useful in this context. Moreover, there are alternative approaches you can explore. Using union find, or disjoint set union, is a great way to group elements and propagate rank changes, but keep in mind that this method requires additional space for parent and rank arrays. Another option is a priority queue or heap-based approach, which is efficient for iteratively extracting minimum or maximum values. However, managing row and column constraints with heaps can be tricky. Finally, techniques like DFS or BFS can be employed for local ranking when dependencies are localized. While these methods can be effective, they may not be as efficient for larger matrices due to recursive or iterative overhead. Each approach has its trade-offs, so understanding their strengths and weaknesses will help you choose the best one for the problem at hand. To wrap up, we reviewed the brute force approach to solving the rank transform of a matrix problem, focusing on its iterative nature. Key takeaways included the importance of analyzing grid-based problems and optimizing for constraints. Thanks for watching, and don't forget to like and subscribe for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!